Hello everyone. In this video we are going to have an example of designing a controller using the Root-Locus approach. The example that we have is regarding an antenna control system. In terms of the modeling, over here you can see the antenna system. There is a potentiometer to determine the desired azimuth angle input for the system. Then we have a potentiometer, another potentiometer to measure the actual azimuth angle of the antenna system. There is a differential amplifier and power amplifier which receives the desired azimuth angle input and the actual angle and then compares them with each other. Afterwards, we have a motor which receives the command from the differential amplifier and the power amplifier, and then depending on the signal that the motor receives, the azimuth angle of the antenna will be changed. It will be updated. So basically it's a closed loop control system. And now we are going to design a controller for this system. Over here we have the block diagram system or a schematic of the antenna system. You can see the transfer function for the power amplifier, which is equal to K1 over S plus A. We have the differential amplifier in terms of a gain. Then over here we have the potentiometer for receiving the desired azimuth angle input. And there is the second potentiometer over here which reads the actual angle from the antenna. And here we have the internal structure for the antenna system. Okay. So I'm not going to go into the details of the system itself, but I'll show you the kind of final model that we have for the system. We have the power amplifier again over here, the preamplifier. Then the motor and load will be shown in this form as a transfer function. Then there is the gain for the gears and we have the K for the potentiometers. If we combine all the blocks with each other and substitute some specific numerical values, we can consider the standard control loop that we had with the planned transfer function given here. GP of S equal to 6.63 over the denominator, which has 3 poles. One at the origin, one at minus 1.71, and one quite far from the origin at minus 100. Now, instead of the preamplifier K, we will insert an analog circuit as the compensator or as the controller. So the analog circuit that we are going to use to design and use will realize the control action. And it will have the transfer function GC of S that we are going to design. So our aim would be to design the controller or the compensator. The design requirements are given here. MP should be smaller than 25% for the step reference. We need to have settling time 2% smaller than 2 seconds for the step references. For response to a unit ramp reference, we need to have steady state error smaller than 0.05 and the controller must be physically realizable. So we cannot have the ideal PID controller or the ideal PD controller. We will take the step-by-step approach and first we will verify if we can solve the problem using a proportional controller, because the proportional controller is the simplest kind of control that we could have. And then we see if it's not possible, we will use more complicated solutions if needed. So as the first step, you would need to draw the root locus for this system. I will draw it for the positive locus. We have one pole at the origin, one pole at minus 1.71, and a third pole far at minus 100. So the third pole is quite far from the others. But if we draw the root locus for the system, we will end up with something like this. So we will have 3 branches. One will go towards infinity, toward minus infinity on the real axis, starting from minus 100, and the other 2 will behave like this. We would need to translate the transient requirements into regions for the MP and set for the overshoot MP and the 2% settling time. If we do so, we will have this kind of desired regions. So this one will be for the settling time, and then for the overshoot, you would need to take the intersection of the 2 into account. So we would need to place the closed loop poles of the system in this area. Alright, so to be precise, I will use the MATLAB and the RL tool function that we have. I already have the GP declared here. GP is ZPK of there are no zeros, so here we have nothing. We have one pole at 0, one at minus 1.71, and the third one at minus 100, and 6.63 is what we have as the rho or k for this system. Then using RL tool of GP, we have the Root-Locus plot shown for the system, and you can see that it is similar to what we have. We will focus on the part of the Root-Locus which is closer to the origin, so I will change the limits for the real axis. Instead of having it from minus 350 to 150, I'll go from minus 5 to plus 5. And from minus 50 to 50 for the y-axis. Okay. So now if you look at this, and keep in mind that we have the third branch going from minus 100 to minus infinity. However, if you look at this, you can see that using a proportional controller, if we change the value of the gain, we will never be able to achieve indeed the transient requirements, because with the proportional controller, the dominant closed loop poles will never be in the white area, which is the desired one. Okay, we can also have a look at the step response of the system. You can see that we, depending on the value of k, obviously, there will be a given value for the overshoot and the settling time. But since the dominant closed loop poles are not inside the white area, which is our desired area over here, we already know that for any value of kp, the proportional gain, the transient requirements will not be satisfied. So we would need to use another type of the controller. And I hope you already know which kind of controller we need in this case. On the other hand, in order to satisfy the steady state requirement, which is on the steady state error for the ramp input, we need to have L tilde, which is equal to KV, bigger than or equal to 1 over the desired steady state error, which is equal to 20. And this will be the case when we don't increase the type of the system. If we don't insert an integrator in the controller. If we don't use the integrator, we will have a type 1 system. For type 1 system, KV will be equal to limit of S times L of S as S goes towards 0. And this will be equal to limit of S times GC times GP. For GP we have 6.63 over S times s plus 1.71 times s plus 100. If we simplify it and replace s with 0, kV will be equal to GC at 0 times 6.63 over 171. And since steady state error is equal to 1 over kV, and we want to have it smaller than or equal to 0.05, so we want to have 1 over kV smaller than or equal to 0.05. This means that kV should be bigger than or equal to 1 over 0.05, which is equal to 20. Okay, so kV should be bigger than or equal to 20, and this is equal to GC at 0 times 6.63 over 171. And out of this, we will get GC should be bigger than GC at 0. Let me correct it. GC at 0 should be bigger than or equal to 515. It's written here as well. GC at 0 should be equal to or bigger than 515.84. This could be obtained or achieved using a lead compensator or maybe using a lag lead compensator. Eventually, it could be also obtained using a proportional controller, but if we use that value for the proportional controller, our system might become already unstable. And on the other hand, the transient requirements will not be also satisfied. So that's one approach. Without increasing the type of the system, we can use a controller with the DC gain which is bigger than 515.84, and then we obtain we satisfy the steady state requirement. The other approach would be to use an integrator in the controller. Then the L of S would become type 2, and then steady state error will be equal to 0 for a ramp reference. In this case, we can use a PID controller because we have a pole at the origin, and then we will not be worried about the steady state requirement. We would need to focus on the transient requirements which are overshoot and the settling time. We can take both of the cases into account, but for now we will continue with the second option. Okay, so we will introduce a controller at the origin. We will introduce a pole at the origin. Sorry. So our GC of S. Our GC of S will have a pole at the origin, or it will have an integrator, and for the 0 we will locate it, or we will place it close to the origin at minus 0.01. So in this way we are expecting our Root-Locus not to be changed a lot indeed. Okay, and then we will be happy with the steady state behavior. So the steady state requirement will be automatically satisfied. Then in order to improve or in order to satisfy the transient requirements, we would need to insert a lead compensator, because we know that the Root-Locus branches will not enter into the desired white area that we had. In order to move the branches into the desired area, we would need to introduce a lead compensator. We can try to do it using MATLAB. You can indeed try to see how placing a 0 and pole for the lead compensator would work. I hope you already know the approach to take analytically. First you can place a 0 using the angle criterion or angle criterion that we have for the system, which is equal to angle of n over d is equal to angle of minus 1 over rho. Using this, we can start by an ideal PD, find the location for 0, and then adjust the location of the 0 and find the location for the pole. Okay, so you can do this analytically as well, and also using the Root-Locus tool, which is RL tool. You can try multiple indeed different cases, and you should also keep in mind that there will be not a unique solution. You might end up with different solutions. One of them is shown here. We can place the 0 of the controller at -8 and then the pole of the controller at -100. And then we would need to adjust the gain in order to place the poles of the closed loop system at the desired locations. And the adjusted gain will be equal to 13,750. Therefore, the overall controller that we have will have this form. So you can see that it has a pole at the origin, S, and a pole at -100, and there are 2 zeros. Over here I have created the controller, GC1. Then we have the closed loop system as T1, which is feedback of GP times GC1 and 1. And then with the step command we can depict the step response of the system, of the closed loop system. Here we have it. If you look at the characteristics for the peak response and the settling time, both of them are satisfied. Settling time is 0.7756 and the peak response is 1.25, meaning that the overshoot is almost 25%. And in terms of the steady state behavior, since it's a type 2 system, it is already satisfied. So all the requirements are satisfied and we have ended up with a second order controller in it. Yeah? Now, as an alternative, we can check if we can avoid using the integral action. If we simply remove the integrator and the 0 which comes with it at -0.01 and then adjust the gain in the events form in order to end up with the closed loop poles at the desired area, our controller will have this form. GC of S will be equal to 14,500 times S plus 8 over S plus 100. We can check that GC at 0 is equal to 1160, which is bigger than the required value. As a result, the steady state requirement will be satisfied. And we can also check the transient requirements. Let's have a look at the step response this time. We have the peak response with the overshoot smaller than 25%, and the settling time is smaller than 2 seconds, 0.717. So all requirements are satisfied. In this case with a simpler controller, and obviously this controller, the second one that we have over here, is preferable over the first one because it is simpler, yeah? And both of them are are indeed proper controllers in order to satisfy the requirements, the transient and the steady state. But if you want to choose one of them, you will go with the second one because it is simpler. So once again, you should know that in designing the controllers, we will not end up with a unique solution. There might be different solutions which satisfy all the requirements. Finally, over here, we will have a look on how we can physically realize the controller. As an example, here we have a lead lag compensator implemented using an operational amplifier or op-amp, a given number of resistors and capacitors. By choosing proper values for the capacitors and for the resistors and putting them in the proper configuration, the transfer function between the output and the input in the Laplace domain will give us the GC of S, the transfer function for the controller. You can try to find it indeed. It will be in the form of S plus Z1 times S plus Z2 over S plus P1 times S plus P2, because this is a lead lag controller with a gain. Alright, but for the purpose of this course, we will not go into the details of how we can implement the controllers. It's enough for you to know the way in which the controllers could be implemented up to this point. We will focus only on designing the controllers in this course. Alright, so that's all for this video. Thank you for watching, and see you in the next video where we will talk about the notch filters. Bye for now.